All right, hello everybody. This is the second in this series of short lectures on EEG. We started by talking about the real basics of EEG when it was first sort of reported, first observations, and the basic principles of electricity in the brain. Today we're going to talk a little bit more about the specifics of how to record EEG and some applications of EEG. So what do you need to record EEG? Well, as we've talked about, EEG is of course recording now the voltage potential at the scalp surface. And so you need a recording electrode to actually record the EEG, and this has to be made of some conductive metal. It's very common to see silver, gold, tin. In some very extreme cases, as in the MRI scanner, you might even see non-metallic electrodes. And this recording electrode is mounted on the scalp surface. It's not exactly on the skin. It doesn't actually touch the skin. There's a thin layer of electrolyte between the electrode and the skin surface, and we'll talk a bit more about that in a second. So you need this recording electrode. Then you need a ground somewhere on the head space where the circuit kind of concludes. So if electricity is generated within the brain and the electrode records that voltage potential, that creates current in the electrode, current in the wire connecting the electrode to the recording system, eventually that current has to ground back out. And the safest place for that to ground back out is back on the head space, so that you get a relatively narrow flow of electrical current. This completes the circuit, so ions flow through the electrode, this flow is measured, potential is calculated, and the ions flow to ground. But if we just measure electrical potential in reference to ground, we pick up a lot of static electricity generated by friction. So your environment around you always has static charge. So if we refer to ground, we'll find that the electrode, the recording of the electrode, will carry a lot of this static charge. And this static electricity can be quite strong. So you know the trick when you shuffle your feet on carpet. This degree of electrical potential that's created by static electricity, this accumulation of static charge, is far, far greater than the EEG that we're trying to record. And the way we get around this problem is by having an additional electrode, a reference electrode, that records the potential at another location on the head. And then what we end up doing is looking at the difference between the recording electrode and the reference electrode, where both are grounded out in order to complete circuits. So the static charge at the recording electrode and the reference electrode will be the same. So that means the difference between the potential recorded at these two electrodes will reflect locally created electrical activity, that is brain activity in our case. And we do this using what's known as a differential amplifier. So EEG amplifiers are differential amplifiers, and they amplify thus the difference in signal between the recording electrode and the reference. So this reference electrode that we use is actually quite important, and you'll see some examples of reference electrodes here. In this case, we have a reference electrode that's mounted on the skin surface right behind the ear, and if you touch the back of your ear, you'll find that there's a very big bone there where your jaw mounts into your skull. And so we use this position because that bone is highly insulating, and that keeps it, there's not a lot of brain activity picked up at this reference electrode. If we then record at a recording electrode here up at the top of the head, we'll get brain activity local to that, where we have relatively little brain activity here emerging in this reference electrode because of this big insulating bone in behind the ear. Another option is to use the earlobe. So here we have a clip electrode on the earlobe, again because there's very little brain activity coming out in your earlobe, of course, right? So now when we record from another position in the head in reference to this earlobe position, we get brain activity at the recording electrode and no brain activity at the reference electrode. So here's how that sort of works. We clean up the earlobe, and then there's an electrode clipped onto the earlobe. Most of the time myself, I use mastoid reference on either ear, so I record from either ear as my references for EEG. And the reason that we're trying to do this is because EEG is very, very sensitive to noise, right? So one of the reasons why we're trying to use this differential amplifier using a reference is because, of course, EEG is very, very small, and that static charge is large, and it will overwhelm the signal. There are other sources of noise. So even if we do have this reference electrode and this recording electrode, where we're looking at the difference between those two proximal electrodes, noise can still impact the signal. Because EEG is so very, very small, it has a magnitude of about 1/100,000th of a volt, and event-related potentials are even smaller than that. We'll talk about ERPs a bit later on. The EEG signal has to be amplified about 50,000 times before it can be measured and sort of worked with. And so that means a very, very small amount of noise, of electrical noise, will entirely overwhelm the signal. And where does this noise come from? Well, pretty much any electrical engine, any electrical motor, or any conductance through wires in the wall, or any electrical source that's around the EEG lab at all will create noise in the EEG signal. And the reason for that is because current flow through a medium with resistance creates a magnetic field, right? So we talked about this earlier with the right-hand rule. Whenever you get current flow, you get an associated magnetic field. And then the issue is that whenever you have an associated magnetic field, any other conductor that comes into that field will start to require charge and will induce current in the other conductor. So here's an example of that. We have current flowing through conductor number 1. Conductor number 2 is sitting passively within the magnetic field that's created by the current flow in conductor number 1. Conductor number 2, because it is in that magnetic field, will have induced current flow. And that induction of current flow, if that was an electrode, an EEG electrode, will of course create current flow on the EEG recording that is not associated with brain activity and therefore is considered to be noise, okay? So that degree of noise created on an EEG by, say, a classic one is the air conditioning unit on the roof of your building housing your EEG lab. That air conditioning unit has a massive electrical engine in it to compress air, and that electrical engine creates an associated magnetic field that by the time it reaches your EEG lab is very, very small, but is sufficient to create noise that will entirely overwhelm your recording of EEG. Another example is somebody is running a vacuum cleaner in the lab next door to your EEG lab, and again, the electrical engine in that vacuum cleaner can create noise in your recording. In order to reduce noise, we use this differential amplifier, so that's one thing that helps reduce the impact of external noise. And if the sort of external noise influences both the recording electrode and the reference electrode equally, the differential amplifier will effectively subtract the noise away. But the trouble is that you always have this sort of distance. If you're closer to a wire in a wall that's creating an electrical field, one electrode is closer, one electrode is farther away, then you'll get this difference in noise, and the differential amplifier won't be able to negate the problem. One thing that helps a lot is by having EEG participants in a Faraday cage, and you'll see this very often in EEG labs. You won't notice, it won't look quite like this sort of the wire mesh, but in the walls of the small room where the EEG amplifier and the subject sits, the walls are entirely encased in fine metal mesh. And the reason for that is that metal mesh is connected to a ground, so any magnetic field, voltage potential field that hits that metal mesh surrounding the room grounds out and therefore does not enter the room to interfere with the recording, to interfere with the electrodes. Another thing you can do is filter out. So sometimes the activity that's created by external electrical sources has specific frequency components. It can be very, very fast oscillations, for example, whereas brain activity doesn't oscillate that quickly. So this sort of activity that's induced by external sources will have a frequency structure that is unlike brain activity. And so we can use filters in order to remove that high frequency component from the underlying signal, leaving only the underlying brain activity. All right, some final comments on the sort of recording of EEG and the principles of EEG. EEG has horrible spatial resolution, right? So we kind of understand this, that because we're looking at electrical activity created within the brain, the conductivity of brain space changes as a function of how much, what type of matter there is in the brain space. Cortex is different than white matter, is different than the meninges, is different than skull. So it's impossible to really figure out the rate of volume conduction in the brain space. Moreover, the skull filters out a lot of the signal because it's very non-conductive. There are holes in your skull, in your eyes and your ears, and these let out a lot more of the signal. You have leakage, signal leakage out your ears and your eyes. And those show up on electrodes that are closer to your ears and eyes. They will pick up signal that leaks out of those holes that doesn't reflect activity that's immediately under the electrode. So it's very tough to infer the location of activity from an EEG signal. But, and here's the big benefit of EEG, electricity travels at the speed of light. And that means that EEG effectively reflects a real-time representation of activity. And this is the big contrast with blood flow related brain imaging, like MRI, bold, blood oxygenation level dependent signals, or PET, which is looking at radioactive tracers in the bloodstream. Anytime that you're looking at blood flow in the brain as a proxy for brain activity, you know that blood flow has a delay. It's about 6 seconds delayed, and that there's also variability in that delay. So it's very, very difficult to infer from blood flow based neuroimaging when brain activity occurs. So EEG gives you exactly when brain activity occurs, whereas these blood flow sort of based methodologies, these tell you more about exactly where in the brain space the activity is, but they really don't tell you anything about the temporal pattern with that data. Okay, so So now we have an idea of how to record EEG, what we're recording. We have some idea about what the benefits of EEG. So we're interested in the time course of a signal, time course of a brain process. What can we do now with EEG? Well, let's start by talking about some clinical applications. One very well-known clinical application, very commonly used clinical application, is to take EEG in an epileptic patient when epilepsy is not responding to medication and surgery is an option. So in a severe epileptic cases, the seizure tends to come from one discrete area of brain, right? So with epileptic seizures tend to be sourced at one particular focus in brain space. And in severe epilepsy, when it's not responding to drugs, one surgical option is to ablate, is to cut out the part of the brain that's malfunctioning that creates the seizure. Now, every time these patients have a seizure, it's creating brain damage. So the brain damage that's created by having to ablate that focus of the seizure is a much better option than allowing the seizures to continue. What you could do in that case is then record EEG from a set of electrodes across head space and try and infer from the temporal resolution or the temporal pattern of activity across the different electrodes where in the brain space that seizure is starting from. So you can see here, for example, that this particular seizure that you're seeing emerge in this data, it onsets earliest at T6 and T5, which are electrode locations over the lateral temporal cortex, so on either side of your head, right above your ears. And so the idea here is that, okay, because this seizure is first emerging in these sorts of areas and only emerging later at other areas over other electrodes, the source is probably somewhere close to these electrodes, reflected in that sort of area. So with very high density electrode arrays, and then subsequently sometimes with electrodes actually inserted underneath the skull into brain space, clinicians will try and figure out exactly where the seizure is sourced to allow them to pursue surgical options for these patients. So here's an example of how that might look, right? So here's a spike that's elicited in brain activity. We have an epileptic spike, and then we can use the pattern of this signal across many, many electrodes to infer where in brain space that spike might be sourced from, right? Here's an additional spike where they're trying to source two different spikes, and they're finding, okay, well, they're starting to get some localization of the underlying disorder. EEG is also, of course, used a lot in sleep research as a way of looking at the current brain state of people while they sleep. So you can do spectral analysis on ongoing EEG, and what you'll find is there's different frequency components to EEG based on the current state that a person is in. When people are sleeping, you will start to see these sort of specific aspects of brain activity that only occur during sleep, and then later this sort of slow wave sleep. There is some of you may be taking a module, I believe, in the coming semester that looks at this quite extensively. Another clinical application is for the use of neurofeedback. So this is the idea that by allowing individuals to learn how to control their brain state, this might have some therapeutic worth. This has been looked at a lot with disorders like ADHD in children. So having children work with neurofeedback environments where you look at a particular aspect of their brain activity and that is fed back to them in some sort of way. In this case, it's fed back in the characteristics of this natural scene. So if the child or the patient or the subject learns how to control the state of their brain, they get some feedback on that ability to do so. And this is thought to, in some cases, allow them to gain control over their disorder or gain control over the symptoms of their disorder. There's a lot of debate about the efficacy of neurofeedback. It's an interesting area of research. There's not a lot of conclusive data at this point. It may or may not work in some situations and not in others, but it's certainly an interesting area of work. So EEG, as we've already kind of talked about, reflects activity in many, many brain areas, right? So electrical fields from strong sources of activity far from the electrode site will summate with fields from sources close to the electrode site. So the signal reflects everything your brain is doing, and your brain is doing a lot. So that leaves open the possibility you want to isolate specific activity related to some cognitive process, right? So if you want to actually now, instead of looking at all of the brain, all of that brain activity that's involved in all of the underlying processes, all of the underlying cognitive processes at any point in time, you might want to isolate the specific activity related to some specific cognitive process. And the simplest way to do this, the simplest way to isolate brain activity associated to some specific cognitive process, is known as computing event-related potentials. And the idea here is that if we time lock ongoing EEG to a repeated event, we can average across all of the repetitions. And when we average across many, many repetitions, all of the brain activity that is unrelated to the time locking event will be considered random effectively. You know, the signal can be as much up or down at any individual moment, right? All of this other brain activity that's not associated to the processing of the time locking event will eventually average out, leaving only the evoked activity that's associated with the event to which we've time locked. So that's why we call these event-related potentials, because they're the potentials, the voltage potential in the brain that's only associated to the time locking event. They're related to the event. And in the next short talk here, we're going to talk at considerable more length about the use of ERPs in clinical research and in clinical applications and also in research applications. Thank you very much.